Henry Ford said, "Engineering is the art of making the impossible possible." But how did weapons of destruction turn into technologies that save lives? And why did American engineers joke that if a bridge doesn't fall, it means they wasted too much material? From dancing bridges to machines searching for God. Right now, a history of engineering feats that will take your breath away. The history of human civilization is, in essence, a chronicle of engineering thought. From the first attempts to tame fire to the creation of giant megastructures that change the planet's landscape, engineers have always acted as the architects of reality. The evolution of engineering thought has come a long way from simple ancient inventions to modern technological miracles, and the main driving force of this process has always been speed, courage, and the ability to solve problems that seemed impossible. Looking at history through the prism of technology, we see that war and peaceful construction often went hand in hand, pushing progress forward. A striking example of how military necessity accelerated engineering solutions is found in the events of World War II. Reliable historical facts testify to the incredible efficiency of American military engineers of that time. In combat conditions, when every minute cost lives, they managed to erect pontoon bridges in just 9 hours. This phenomenal speed allowed heavy tanks to cross rivers without delay, maintaining the pace of the offensive and changing the course of battles. This demonstrates how extreme conditions mobilize engineering genius to create solutions bordering on fantasy. No less interesting is the story of the appearance of tanks themselves, which became the symbol of military power in the 20th century. Few people know that early prototypes of these machines, inspired by Caterpillar track ideas, were tested in an atmosphere of strict secrecy. In 1914, in British laboratories, engineers used a trick to hide the true purpose of their developments from enemy spies. They disguised the combat vehicles as harmless water reservoirs. It is from here that the name tank, container, cistern originated, sticking in world languages as water tanks to deceive enemy intelligence. Henry Ford, the man who changed industry, once very accurately noted the essence of this profession. Engineering is the art of making the impossible possible. This quote perfectly describes the spirit of inventors who are not afraid to challenge the laws of physics and the skepticism of society. Engineers are people with a special mindset, capable of seeing structure where others see chaos. There is an anecdote that an experienced engineer, looking at his creation, allegedly said, "If the bridge doesn't fall, it means we built it too strong. We wasted materials." This joke, for all its irony, emphasizes the eternal search for balance between safety, economy, and efficiency, which lies at the heart of any great project. Diving into the history of the 18th and 19th centuries, we discover an era when mechanics laid the foundation for future industrial and military breakthroughs. This period is often associated with Western achievements, but a closer look reveals little-known pages of Russian inventions that had a significant impact on global engineering but often remained in the shadows. We explore how domestic engineering thought was ahead of its time, creating technologies that would later become the standard worldwide. One of the most impressive examples of being ahead of the curve is the work of Rodion Glinkov. A reliable fact states that back in 1760, this outstanding mechanic created a water-powered spinning machine. Glinkov's invention was not just a step forward, but a real technological leap. The machine increased labor productivity by 15 times. What is particularly remarkable is that this happened 11 years before similar devices appeared in England, which is traditionally considered the birthplace of the Industrial Revolution. This fact vividly illustrates the potential of the Russian engineering school, capable of generating advanced solutions long before their mass introduction in the West. No less intriguing is the history of the development of the Caterpillar track, a technology without which it is impossible to imagine modern construction and military equipment. The focus turns to the figure of Captain Dmitry Zagryarski. There is a persistent rumor, supported by some historians, that in 1837 Zagryarski developed the principle of Caterpillar tracks under the influence of secret military orders. Although officially the patent and development were attributed strictly to agricultural needs to improve passability in fields, the shadow of military application hung over the project from the very beginning. This assumption seems quite logical, given the strategic importance of mobility in the conditions of Russian off-road terrain. Confirmation of the significance of Zagryarski's ideas is found in a little-known fact about field tests of his invention. Zagryarski's tracks were tested on prototypes capable of pulling heavy artillery through impassable swamps. In essence, these experiments anticipated the appearance of World War I tanks, proving the effectiveness of Caterpillar traction in extreme conditions, long before armored vehicles entered the battlefields of Europe. This was the technology of the future, realized in metal in the mid-19th century. The interpretation of this historical data leads to an important conclusion. The Russian engineering school in this period did not just keep pace with the times, but often surpassed Western colleagues in the boldness and originality of solutions. The inventions of Glinkov and Zagryarski illustrate the huge intellectual potential, which, unfortunately, was often forgotten or did not receive due development due to political storms, bureaucracy, and the complex historical fate of the country. Nevertheless, their contribution to mechanics remained undeniable proof of engineering genius. The 19th century became an era of grandiose infrastructure projects that forever changed the perception of space and time. The main hero of this time was railways and bridges integrated into unified transport networks. A special place in history is occupied by the construction of the Transcontinental Railroad in the USA, a project that not only connected two ocean coasts, but also became a symbol of man's indomitable will to conquer nature. An analysis of this construction reveals a picture of titanic labor and engineering audacity. The scale of the work done is amazing even today. A reliable fact. By the time construction was completed in 1869, this road linked the Atlantic and Pacific coasts, passing through the most difficult landscapes. Engineers had to design and erect 50 bridges and bore many tunnels in rock formations. The result was worth the effort. A journey that previously took months of dangerous travel in covered wagons or on ships around Cape Horn was reduced to a few days of comfortable travel. It was a real revolution in logistics and communication. However, behind the facade of technical triumph lies a little-known fact about the human price of this achievement. The main burden of construction in the most dangerous sections was borne by immigrant workers of Chinese origin. They built bridges and laid tracks practically by hand, using only hammers and dynamite as their main tools. They had to work in inhuman conditions, risking their lives due to avalanches in the Sierra Nevada mountains and rock explosions. Their contribution to the creation of the continent's transport artery remained undervalued for a long time, although it was by their hands that the most complex engineering structures of the route were erected. The history of the construction has become overgrown with legends. One rumor has it that engineers and construction leaders held negotiations with Indian tribes, through whose lands the road passed, in a very original way. Allegedly, miniature, skillfully made models of bridges demonstrating the power and inevitability of the iron horse were presented to the chiefs as diplomatic gifts. History is silent on how effective such diplomacy was, but the image of exchanging technology for loyalty is very symbolic. The significance of bridges in this project went far beyond simple river crossings. The end of the 19th and the beginning of the 20th century were marked by the appearance of icons of bridge building, which became not just transport arteries, but real monuments to human genius. The Brooklyn Bridge in New York and the Golden Gate Bridge in San Francisco, these suspended giants, became symbols of their cities and milestones in the history of architecture. The Brooklyn Bridge, grandly opened in 1883, became a real wonder of the world of its time. A reliable fact states that it held the title of the longest suspension bridge in the world for 20 years. The scale of the materials used is amazing. Creating its load-bearing cables required more than 6,000 kilometers of steel wire. This structure was the first where steel was used in such a volume, proving its reliability and opening the era of high-rise construction. The engineering solutions applied during its erection were revolutionary and largely risky for that era. Half a century later, on the other end of the continent, the Golden Gate Bridge was being erected, becoming a masterpiece of the Art Deco era. Construction over the strait, famous for its winds and fogs, required special safety measures. A little-known fact, a giant safety net was stretched under the span under construction in 1937. This precaution saved the lives of 19 workers who fell down but remained alive thanks to the net. These lucky ones subsequently founded the unofficial but legendary Halfway to Hell Club, which became part of San Francisco folklore. Intriguing rumors also circulate around the Golden Gate Bridge. They say that the bridge dances under the influence of strong wind, deviating to the side by up to 80 centimeters. This flexibility of the design allegedly impressed engineer architects so much that it inspired them to develop the design of flexible skyscrapers, capable of withstanding hurricanes and earthquakes due to the mobility of the frame. Although the amplitude of oscillation is factored into the design, the myth of the dancing bridge gives it a special, almost living aura. The 20th century brought new challenges, and the focus of engineering thought shifted towards military needs, linking together the mobility of combat vehicles and the need to quickly overcome obstacles. Tanks and bridges, seemingly different entities, turned out to be inextricably linked in the strategy of modern warfare. The tank needed a bridge, and the bridge was created for the tank. Military needs dictated their cruel conditions, requiring impossible construction speeds. A reliable fact from World War II confirms that American sappers achieved incredible skill. They built crossings literally in hours. This ensured the continuous advance of tank columns, not giving the enemy time to regroup. The ability to build a bridge under fire became as important a factor in victory as the caliber of guns. Tanks themselves also went a long way in evolution. We remember Zagryajski's early ideas, and a little-known fact confirms that his concept of caterpillar tracks found its embodiment in the combat vehicles of the new century. The British Mark I tank, which entered the battlefields in 1916, became the first practical application of this idea in combat. It broke through lines of German trenches, moving at a speed of only 6 km/h. But for that time, it was the relentless movement of a steel monster, capable of overcoming mud and ditches inaccessible to wheeled vehicles and infantry. The interpretation of these events leads to complex conclusions. Technologies for the rapid erection of bridges and the creation of armored vehicles saved millions of lives of Allied soldiers, bringing the end of the war closer. However, this raises eternal ethical questions about war as an engine of progress. Why does humanity make the biggest leaps in technology when it seeks to destroy its own kind? Moving to the post-war era and modern times, we see how engineering genius switched to solving global problems of energy and fundamental science. Modern megaprojects surpass everything created earlier in their scale, demonstrating the capabilities of 21st century technologies. One of the greatest achievements in the field of hydropower is the Itaipu Dam. A reliable fact: launched at full capacity in 1991, this colossal structure generates 14,000 MD of electricity. The capacity of this station is so great that it provides the lion's share of electricity needs for two countries at once, Brazil and Paraguay. The concrete spent on its construction would have allowed building 210 stadiums similar to the Maracana. Itaipu is a monument to how engineering is able to ensure the vital activity of entire nations. At the other pole of engineering thought in the field of subatomic particles is the Large Hadron Collider, LHC. A little-known fact reveals the incredible complexity of this device. Launched in 2008, the collider is a ring of 27 kilometers of tunnels stuffed with superconducting magnets. To operate these magnets, a cooling system is required that maintains a temperature of 200 °C, which is colder than in open space. This is the largest and most complex machine ever created by man, designed to recreate conditions that existed moments after the Big Bang. Many rumors circulated around the LHC, especially in the scientific community. They say that engineers and physicists working at the collider allegedly heard signals from Bose-Higgs particles, the so-called God particle, much earlier than the official announcement of the discovery. Completing our review, we approach the section that summarizes everything said and inspires reflection on the future. The path from the first wooden mechanisms and tanks to gigantic bridges and particle accelerators is not just a history of iron and concrete. It is a history of the evolution of the human spirit. We reflect on how engineering solutions, born in the flames of wars or in the silence of laboratories, radically changed the life and worldview of society. The legacy of engineering geniuses surrounds us everywhere, often in things we take for granted. Sometimes the greatest discoveries happen by chance, as a byproduct of other research. The microwave oven, without which it is difficult to imagine a kitchen today, was invented by chance in 1945. Engineer Percy Spencer, working with military radars, noticed that magnetron radiation melted a chocolate bar in his pocket. This discovery, coming from the sphere of military defense, forever changed the lives of billions of people, accelerating the pace of life and simplifying cooking. Interpreting the entire path traveled, one can say that the main feature of engineering is resilience. We learn to build not only fast pontoon bridges for momentary needs, but also eternal dams capable of serving for centuries. Engineering teaches us to adapt, transfer technologies from one sphere to another, and find ways out of hopeless situations, Looking into the future is impossible without recognizing the role of those who create the material basis of our world. As the great visionary Nikola Tesla said, "The future is built by engineers." This quote serves as the ideal final chord. It reminds us that as long as there are problems requiring solutions and dreams requiring realization, engineers will continue to create their miracles, turning the impossible into reality. If you liked the video, the best gratitude is your like and subscription. This helps us make content of even higher quality. And in the comments write, about which engineering giant should we tell in the next episode? See you very soon.